Okay, so now I've taught you how to differentiate, and you're all really happy with doing that forwards, backwards, upside down, and in your sleep. What I'm going to show you in this video is how you go back the other way, and that's called anti-differentiation. So think of it a little bit like when we teach you how to expand brackets and how to multiply through the brackets, and then once you've got the hang of that, we teach you how to do it backwards and factorize. It's a little bit the same sort of thing. So sometimes you need to differentiate, sometimes you need to anti-differentiate. It's not nearly as complicated as it sounds. You'll probably have more trouble spelling it than actually doing it. So, anti-differentiation is simply the reversal of the differentiation process. So if the derivative of x cubed is, oh, that should be 3x squared. Excuse my typo. Is 3x squared, then the antiderivative of 3x squared is x cubed. Okay, so we did the whole bring the power down, reduce the power by 1, and then we can do it in reverse. So increase the power by 1 and remove that coefficient. So we use Leibniz notation for antiderivatives. So remember that was when we're differentiating, that's when we talk about dy dx. Okay, so when we're anti-differentiating, you have this funny little sort of curly f symbol, or s, depending on how you look at it. This is the function that you are anti-differentiating, so this is the derivative. Okay, and that's saying that we are anti-differentiating with respect to x. So when we talk about differentiating with respect to x, then we're anti-differentiating with respect to x. Okay, so if you see that, that says anti-differentiate that with respect to x. So in this case, that would be x squared. Now, hang on a minute, because there's a bit of an issue. What happens when we differentiate each of the following? Okay, so we know that here dy dx is 2x, because we just bring the power down. Okay, over here we know that dy dx is 2x, and we don't include 3 because it's constant, so it's just plus 0. And here we've got dy dx is 2x, and again we don't include the constant. So what we've got is 3 different functions, but when we differentiate them, we get the same function, so the gradient function is the same. However, if we were to anti-differentiate that back to here, we would just get x squared, which means you wouldn't have this constant, so you just end up with your standard parabola, where it could be anything up here or down here, as long as it's the same shape. Okay, so we need to take into account the fact that we lose that constant. So because we lose it, we need to account for it by doing this plus c. Now this is the bane of the existence of calculus students the world over. It's the kind of thing that you always forget in the exam, and then you lose a mark for it. So get it into your head right now, tattoo it on your hand, write it on your friend's forehead, so when you look at them you can see it. Always remember plus c when you are anti-differentiating. Okay, so that just takes into account the fact that we know we lost a constant, and there could be a constant term, and we don't know what it is, unless we have more information. Okay, so we can also call an antiderivative an indefinite integral. Okay, saying that's not a lot better than saying antiderivative. They're all pretty big words, but get used to it. So the textbook talks about indefinite integrals as well. So the general rule of thumb, because the examples we've done so far have been fairly straightforward, but the general rule for anti-differentiation is that if you're anti-differentiating x to the power of n, you need to increase that power by 1, but then you also need to divide by that increase, because remember when we bring that down, we end up with coefficient out the front, and you need to divide by that coefficient to get rid of it to end up with this. So I'll show you a couple of examples just to get that clear, because this notation looks a little bit confusing, but it's actually really straightforward. Don't forget plus c. Okay, so let's do this one. We've got find the general antiderivative, or the indefinite integral, of each of the following. Okay, so using Leibniz notation, we're going antiderivative of 3x to the power of 5 with respect to x, so dx. So we don't do anything with 3, we just leave that. X, we increase the power by 1 to the power of 6, and then we divide by 6. Okay, now we can cancel those, and we end up with x to the 6 over 2, and what have I forgotten? Plus c. Always have your plus c. Okay, if you don't do it here, you'll forget to do it down here. You can always check. So similar with similar to factorising and expanding, you can now differentiate this and see if you get that. So if we brought the power down, we'd get 6x to the power of 5, 6 divided by 2 is 3, 3x to the power of 5, correct. Okay, so you can always check whether you're right or not. The next one, so we're integrating, sorry, not integrating, anti-differentiating. Integrating comes later. 3x squared plus 4x cubed plus 3 with respect to x, okay? Now, increase the power by 1. Alright, and I know that x cubed, the derivative of x cubed is 3x squared, but basically what we're doing is that. So we had 3x to the power of 3 divided by 3. Then we've got 4x to the power of 4 divided by 4, and then we're just adding an x to this one, plus 3x plus c. Okay, these cancel. So you just get x cubed plus x to the power of 4 plus 3x plus c. So pretty straightforward, nothing too complicated there. Especially if you just do it one term at a time, make sure you divide by your increased power, simplify if necessary. Don't forget plus c. Okay, so we can actually find the value of c if we give more information, such as a point on the curve. So similar to when we have y equals mx plus c for linear equations, if I give you the gradient and then I give you a point on that line, you can find c. So it works exactly the same way. So let's have a look here. Okay, so we've got the derivative of a function is x cubed plus 4x squared, and we know that the value of the function, not the derivative, so be really careful about where the prime is. So this is your derivative, and this is your function over here. Okay, don't mix them up. If you substitute points on the function into the derivative, you'll get into all sorts of strife. Okay, so let's anti-differentiate first. So f of x must be, now increase the power by 1, divide by the power, okay, plus increase the power by 1, divide by that increase, plus c, don't forget plus c, and then use this point to substitute into here and solve. Now you should be able to see that if you let x equal 0, that's just going to be 0 plus c, and we're told that that equals 0, therefore c equals 0. Okay, therefore f of x equals x to the power of 4 on 4 plus 4x to the power of 3 on 3. Okay, so nice and easy there. Remember the plus c, substitute your point in, and find your original function like that. So remember, if it does say find f of x, don't stop at this point, that's not good enough, you need to actually state what the function is. Okay, and now I'll show you how to do it with ClassPad, because there's always a way to do this with ClassPad. So I'm just going to write this over here so when I put the ClassPad up, I can actually still see it. So we've got the gradient of the tangent at a point, which is just a fancy way of saying the derivative, is 5x. Okay, and there's a point on the curve such that when x is 0, that value is 6. Okay, so the way we do this, start with typing in 5x. Now, going up to calculation, using the little funny curly f thing. Okay, make sure it's indefinite integral. We'll talk about this next year, I think. So indefinite integrals. Okay, and it's anti-differentiated for you. So 2.5 or 5 on 2 times x to the power of 2. Now, what you want to do is drag that down. You want to go plus c. Okay, ClassPad actually doesn't add c for you, so you need to make sure you do that manually, and then define it as a function. Okay, it's now a function. Right, and now we can do a solve. If we go f of 0 equals 6, because we're told that's the case, and now we solve it, advanced solve, and the thing you need to be careful of is changing that to c, because we're now solving with respect to c, not x. And so as you see, equals 6. Okay, so what you've got there then is that f of x equals 5x squared on 2 plus 6. Okay, you can check that by substituting that point in. You can check the differentiating by pulling that down. You get 10x divided by 2 gives you 5x, which is what you had there. So it's all good. So hopefully you can see that that's really pretty straightforward, nothing to be freaked out about. It's just a process. If you can differentiate, you can anti-differentiate, provided you remember to plus C, always add C. I can guarantee some of you are going to forget this in a test or an exam, but I'll keep reminding you anyway. So it's just the reverse. It's also known as indefinite integration. Okay, we talk more about integration next year in the course next year. This is your general formula. It looks more complicated than it is. So basically you just increase the power by 1. Don't worry about whatever's going on with the coefficient. You can just leave that there. So increase the power by 1, divide by that increased power, then you can cancel down if necessary and add C. Plus C there. Remember, plus C.